What I'm going to try to do today is to take you through some of the work that I've been doing thinking about the intersection of deep learning and causality. So all of you in the morning lecture by Rajesh learned a little bit about the basics of causal inference. And what I'm going to try and talk to you about today is realistically three things. And if we have some time, we'll get to the fourth one, but I'm not very optimistic. But before we do that, I think it's worth thinking about why this even matters. And so a lot of the reasons that I care about building out this intersectional space of deep learning and causality is motivated by a project that I'm working on with Rob Grant, who's a medical oncologist at Princess Margaret Cancer Center in Toronto. And the question we really care about is, after someone has surgery for colorectal cancer for recession, should they be prescribed chemotherapy? And now most of you might be wondering, why is this even a question? Like, why don't doctors already have a trial for this? Why don't they know what to do in this case? And what might surprise you is that there's many, many such questions like this that exist in medicine, for which the status quo is effectively to do the thing that the doctor decided to do where they were trained. So if they trained at Harvard or if they trained at Mayo Clinic, they just might have priors on how to operate for such patients that continue to propagate in their practice today. And so we wanted to ask, for this very specific clinical question, can we come up with a way to understand who's going to benefit from chemotherapy? But this question is hard, because in cancer, chemotherapy and the prescription thereof is a complex process that is determined not just by looking at an individual's genetics, but also by looking at the histopathological image. And so we wanted to know whether we can take some of the tools that have been developed in machine learning over the last decade, tools like large-scale neural networks, and leverage them to answer this causal question. But before we do that, we need to think about a few methodological advances that we can make to correct for some of the observational confounding that we find in this data. And so that's going to be the motivation for my talk. And so the remainder of the talk will sort of focus really on the methodology. But you can ask, well, we have incredibly powerful neural networks right now. So can we just use one of those? And so to motivate why even the best set of neural networks that we have right now in the form of GPT-4o is insufficient, I did this really simple thought experiment where I took the image on the right, which is really these two triangles in a circle, and I asked GPT-4o, organize these objects in a way such that if they exist in a two-dimensional plane and gravity acts upon them, there's no motion for these three objects. And so for a human, you can ask, what is the simplest configuration of these three objects that results in no motion for all three under the influence of gravity in the two-dimensional plane? And most of us would come up with this as a configuration. And it seems intuitive that we would come up with this as a configuration. But if you ask this for a model, they come up with configurations that look like this. And at least in the several model examples that I tried this on, all of them came up with incredibly complex conformations of these objects. And so you can ask even similar questions about causality and physics to image generation models. And so in this particular case, I asked it to generate an example of a shovel that no human can ever use. And so what it does is that it creates this complicated twist around the handle, but at the end of the day, I think I could still use this shovel. So these constraints that represent really complex problems for models to reason about physics, about causality, still remain a fundamental challenge, even in the regime of these large language models. But does this really matter in medicine? And so to give you a reason for why you should care about it in medicine, I'm going to talk about Irene, because Irene here loves to eat broccoli. And it turns out that if you eat broccoli, you might not be as and if you were prescribed warfarin, you might have actual counterindications, because broccoli contains a lot of vitamin K. And unless your doctor was capable of doing that reasoning that looks at the mechanistic relationship between vitamin K, broccoli, warfarin, and why a patient should not be prescribed warfarin if they're on a diet of a lot of leafy greens, you're going to have these models struggle to operate in these domains. And so we can hope for the idea that in the next generation of GPT-5, we might have these language models that are capable of causal reasoning. But if we pause for a second and think about what that would necessitate, I think we'd find that it's very unlikely. Because over the last 10 years, one of the biggest advances that we've had is we've realized that over-parameterizing these neural networks and making them do next token prediction has resulted in this class of models. But what we don't really know is what the underlying inductive bias of GPT-4o is. We don't know how it's performing the reasoning tasks that it's doing at scale. And what's more, we don't actually have the ability to control or change how it does its reasoning task at this stage. And I'm going to argue that that's kind of what we need to work towards. And so when I think about this as a fundamental problem, I think about how do we design better neural networks so that at scale, they have the inductive bias of being able to reason causally. And so that's one of the big questions that I'm very, very interested in. So if you're interested in similar things, come talk to me. But what I'm going to tell you about are 3 small vignettes of projects that we've been pursuing that try to tackle much, much smaller problems that hopefully will lead us to potential answer for this much bigger picture vision. And one of them is really about the idea of estimating treatment effects from observational data. And so clinicians are very interested in understanding not just what happens to a patient, but rather what changes as a function of the treatments that they prescribe. But the problem, as you heard about this morning, is that unobserved confounding can make the effect estimation problem very difficult. But in reality, if I know that a treatment has a positive effect, I as a clinician might choose to prescribe this treatment. I can come to the exact same conclusion if I know that the treatment has at least this much effect, which is to say that I have a lower bound on this effect as a consequence of prescribing this treatment. And Rajesh talked about the idea of relaxing some of the assumptions in causal inference this morning. So what I'm going to tell you about is if instead of solving the causal effect estimation problem, we can solve a slightly different problem, which is that of estimating upper and lower bounds on the causal effect estimate, perhaps that will suffice in order to be able to give us a tool to conduct decision making. And so this project that we worked together with Vasilis on was really brought about by thinking of how do we take the problem of effect estimation and translate it into a problem of what's known in the causal inference community as partial identification. So instead of exact identification of the causal effects, you're going to partially identify both the upper and the lower bounds on this effect. And so, if you zone out for the next few minutes, at least for this portion of the talk, here's really what you should take away, which is that causal effect estimation is usually impossible, but there's some instances where you can obtain these bounds. And so I'm not going to go into a lot of technical depth about what they are, but you should at least convince yourself that these bounds have meaningful utility for decision making, and that getting those bounds from observational data, if doing so is capable under the relaxed set of assumptions, is actually advantageous to us because it continues to help us make these decisions. And so what the contributions of this work are is a new method to leverage deep generative models to calculate these bounds, and one that enables us to go beyond linear treatment effects. And so we'll focus in on this problem of partial identification really in the instrumental variable setting. And so you saw this graph, or one that looked very similar to it in the morning, and it's really the idea that we want to estimate the effect of treatment T on outcome Y subject to the existence of some instrument Z and unobserved confounding U. Now, if all of the relationships between these random variables, between U and T, U and Y, T and Y, Z and T, are assumed to be linear, then more than 20 years ago, Balker and Pearl came up with a method to bound treatment effects. And effectively what they did is that they used a linear program in order to create these bounds. So let's look at what this linear program actually says. So at the top is a min and a max over the individual level population of the potential outcome yt. So what it's saying is that in order to find bounds on the treatment effects, you're going to maximize the potential outcome and minimize the potential outcome subject to this distributional constraint. And if we look at what this distributional constraint actually is, all it's saying is that I need you to create the parameters of my linear generative model. Remember, Balker and Pearl was in the linear case, such that the distribution of my observed random variables satisfies the marginal under the unobserved random variable. So what this linear, so in the linear causal model case, you can transform the problem of partial identification into the solution to a linear program. But the problem here is that as the cardinality of your observations grows, the linear program blows up in size. And so it becomes harder and harder to actually solve this. And there's no natural generalization to this in the nonlinear setting. And so this transformation of this problem to the nonlinear setting is what we wanted to study. And to do this, we needed 3 ingredients. So we needed to change the way we represented relationships between random variables. And in order to do that, we used a class of models called implicit generative models. And these, in another world, are referred to as neurocausal models. And so this is sort of building on a rich line of work by Elias at Columbia. And we're sort of adopting their framework of using implicit generative models to represent the relationships between random variables. So that lets us represent the relationships between the x, t's, and y's. We use them, we model them via a deep generative model. The next 2 things we need, and this is really where some of the contributions of our work kick in, are a method to be able to compute and maximize/minimize the interventional distributions, which is to say perform do calculus in this class of implicit generative models, and satisfy this distributional constraint. And so for the second one, what we do is effectively use tools from PyTorch in order to be able to evaluate the counterfactual. So that lets us evaluate what the potential outcome yt is under this neurocausal model. So this is just saying that we can write down a program in PyTorch that lets us write out this expectation of yt under a neurocausal model. Next, for the distributional constraint, we use the one Wasserstein distance that enables us to model that enables us to make sure that the parameters of this implicit generative model match the statistics of the observed distribution. And after that, the intuition for the optimization problem that we actually solve is very similar to what Parker and Pearl did 20 years ago, except adapted using many of the modern tools in deep learning. So we're solving this min-max optimization problem that is subject to this distributional constraint. And in practice, we solve this via solving the Lagrangian. But the intuition that I wanted to give you is really represented by this weird-looking figure here. What you're doing when you solve the distributional constraint is that you are searching in the space of all valid distributions of the parameters of your implicit generative model such that the distributional constraint is met. And within that space, which is a highly complex non-convex space, you are attempting to find the parameters of this implicit generative model that maximize the ATE and minimize the ATE. And once you find those 2 sets of models, you're done. Because the max and the min form these bounds on the treatment effect that you set out to estimate. So that's really the intuition that I wanted to give you for this line of work. There's a lot more subtleties about when this optimization problem actually works and how to solve some of the technical irregularities with it, but I'll defer you to the paper on reading up about that. And we tried this out on a variety of different causal graphs, both discrete and continuous, because this class of methods and models is very general and largely works in both cases. And what we found is that we're able to match the optimal bounds on the ATE in the case of instrumental variables. And at least relative to prior work, we're able to get valid bounds on what are called dose response curves, which effectively characterize the treatment's effects corresponding to continuous value treatments. So in summary, this method is sort of a catch-all in terms of being able to handle both discrete and continuous value treatments. And it lies much more on the right-hand side of this axis. And so if you sort of read into the literature in causal inference, there's a lot of really rich work on linear causal models for which we have excellent theory. And I think one of the challenges there is that as the complexity of our questions grows, as we want to ask causal questions with things like images, large amounts of text data, the current crop of tools are just not going to suffice to answer those questions. And one of the best set of tools that we have right now to deal with complex high-dimensional data are tools from deep learning. But at the same time, I want to highlight that there's no free lunch. Like, we do lose something when we make this transition to this class of models, which is the same level of rigor in theory is no longer accessible to us because we as yet don't have a good grasp of theory for deep learning. And so with that, what I want to do is slowly transition to the phase where I tell you a little bit about how we tackle the problem of not static decision making, but rather sequential decision making. And so this problem can really be distilled into this idea of how do you build systems that learn from experts who know more than you do. So you can ask, why is this relevant for medicine? Well, when you or I go to a doctor, they don't just see us as a set of numbers of lab values. They don't just see the X-ray that was just taken. They notice the kinds of clothes that we wear. They ask us about our day. They ask us about our job. They look at how we dress. And they make subjective judgments that summarize a variety of unobserved data about every single patient, which is to say, your doctor probably knows a lot more about you than they would represent for you in your data. And this knowledge that they use then translates into how they give you treatments. And so the argument here is that if you're learning from such expert data, the kinds of decisions your doctors are going to make is not solely going to be based on your data, but also based on this unobserved set of information that only the doctor knows about you or has inferred about you. And if we think about this learning problem from the perspective of reinforcement learning, then we have two possibilities. We can either do perfect imitation, which might lend us into the problem of ignoring this notion of unobserved confounding, because as a learner, we don't have access to what's in the doctor's mind or their subjective interpretation about our condition. Where on the other hand, if we didn't do any imitation learning, we might have to do pure RL, which is rely primarily on trial and error with a simulator in order to learn to solve a task. And the question we wanted to ask with this framework is there a middle ground? Can we learn from expert level data even when we know that the learner is learning from data generated under unobserved confounding, which in this case are the doctor's subjective preferences about the patients? And so this is another line of work that we've been collaborating with Vasilis on fast and accurate meta-RL, and so there's an arXiv link up about it. And I just want to give you a brief highlight of how we solve the problem. So given expert-level data, which is sequences of decisions made by the expert, we solve an optimization problem to estimate the maximum entropy prior, which is to say, a prior distribution over interventions that the doctor might make that explains all of the variation, but is as compressed as possible. And so we give a non-parametric solution to what this prior looks like, and we use this prior in an exploration algorithm in RL. So that's the high-level picture of what we ended up doing for this work. And to study whether or not this actually made any difference, we studied this on this environment called Deep Sea, where the goal of this game is to get this ship by moving left and right in a finite number of steps to find this treasure. And the treasure keeps moving. And so we can generate expert-level data that knows exactly where the treasure is. So if you knew where the treasure was as an expert, you can navigate this game very effectively. But as a learner, you don't actually know where this treasure is. So you have to come up with a policy function that might help you find this treasure. And so on each of these plots are different instantiations of this game. And as you go from left to right, we're increasing the entropy or the uncertainty of where the treasure is in the bottom 4 panels. And what we find is in most of these cases is that leveraging this expert level data enables us to get a policy function that learns much, much faster than either doing imitation learning or just doing DQN, which is naive reinforcement learning alone. And so I know I'm running close to time, so I want to end on talking about this paper that's part of a recent collaboration with Chris Madison, and this is work that's led by Nikita Dhawan. And so in this paper, we wanted to ask, how do we take advantage of all of the rich natural language data that exists in the world today and use it in order to get causal effect estimates? And so if you think about getting to causal effect estimates from a very practical lens, we have completely randomized experiments, which are very, very expensive to run. We can have observational structured experiments where someone creates a large cohort of individuals to carefully look at and annotate data and use that data within a causal inference pipeline using an estimator such as inverse propensity weighting. And finally, we have observational natural language experiments, which is part of the crux of our focus. So if you think about this process of going to a website like Patients Like Me, where patients report on the drugs that they were given, the treatments that they've been on now and in the past, and the kinds of subjective clinical experiences that they're facing, we can ask, how do we take the self-reported text patient data and transform it into data that can be then used to estimate treatment effects? So the pipeline that we built was exactly this. We would take large amounts of text data that were reported by an individual. We would use a large language model to take this data and identify the relevant features and covariates that were necessary for us to develop a causal effect estimator. Once we had this table of data for each patient, we would summarize them for all patients and run an inverse propensity reweighting estimator that I'll defer the details of this to the preprint itself. And then we would compare this effect estimator that we got from observational data to what was found in the randomized trial. So I want to make two caveats here. The population that the randomized trial was done on was necessarily different from the population that is self-reported all of this information in the form of their subjective experiences. And so what we ended up doing was looking at 3 different trials. Looking at 4 different trials. So for each trial, we took this first trial of semaglutide versus tirzepatide and used it to tune the hyperparameters of our model. And once we had those hyperparameters tuned, we ran the pipeline end-to-end on self-reported data from these 3 remaining trials. And effectively, what we found, which is in NIPW, is that the estimates of causal effects that we identified were within 3 to 4 percentage points of the causal effects from the randomized clinical trial. And so what is this is that we find that this is sort of a verification of the idea that this class of methods is really, really powerful at accelerating the process of hypothesis discovery from large observational data sets. So I'm not going to conclusively say that this is the only way to do causal effect estimation from text data, but we took a process that would have otherwise taken a team of students, maybe an entire summer, and completed it in the context of 2 days. So I think that represents a significant degree of acceleration in performing these kinds of observational studies that a lot of you may find useful. OK, so I'm rapidly running out of time, but I will just briefly highlight this paper, which will conclude the set of my talks, where in the past, what I've talked about is how we can use tools from machine learning in order to solve problems in causal effect estimation, whether on theoretical problems or on more practical problems. But I think causal inference has a lot to give back to the machine learning community as well. And in particular, one of the problems that we were motivated to think about is how we can build neural networks from scratch that were designed to satisfy certain conditional independence constraints. So what does that mean? Well, for those of you who are familiar with tools for density estimation, such as mass autoregressive density estimation, or MAIDS, the way that they work is by parameterizing the chain rule of probabilities. You know that you can represent any distribution via the chain rule of probabilities. And so what MAIDS do is that they learn a neural network-based transformation to go from an input distribution to an arbitrarily complex output distribution. This process for MAIDS is constructed in a very special way. They use weight masking for each of the weights in the neural network, such that when you multiply those weights, you get back a lower triangular matrix. Because if you do a little bit of algebra, what you realize is that the consequence of representing a probability distribution via the chain rule of factorization is implicitly equivalent to having a lower triangular matrix as the product of all your weight matrices. And what we did here was generalize this idea, where we said, what if you didn't just want to have a lower triangular matrix, but what if you wanted to have a sparse lower triangular matrix? How would you be able to support the creation of a neural network with this weight masking structure. So that was a technical problem that we solved. And this technical problem is interesting because now it gives us a completely new set of tools to be able to model arbitrarily complex Bayesian networks. Because any notion of sparsity that you can inject into the adjacency matrix will correspond to a different kind of Bayesian network. And so just to skim through this, we gave a recursive algorithm for computing each of these masks, and we studied a few different kinds of optimization objectives that enabled us to compute these masks effectively, and showed that this kind of method can improve the sample efficiency of causal effect estimators. And so with that, I'm going to conclude and just say thank you to a group of very wonderful students and collaborators who've all sort of led this work and gotten it to this stage. So I'm happy to take a few questions at the end.